Welcome to the deep dive. Okay, today we're exploring something really right at the edge of what we understand physically. The singularity. It's this point where, well, the basic rules of physics, the ones we rely on, they just seem to stop working. Our goal here is to maybe give you a clearer way to think about one of the universe's biggest, most baffling cosmic puzzles.
Exactly. And at its core, singularity is basically a region where density just goes. It's infinite. Literally, gravity becomes unbelievably strong, overwhelming everything else. And the actual fabric of space and time, it curves, well, infinitely. It's where our equations just give up. What's really key here is that these aren't just like mathematical flights of fancy. Albert Einstein's theory of general relativity, which is, our best handle on gravity, it actually predicts these things exist.
Right, and the places we find them, that's where it gets really interesting. Most people think of black holes, right?
Yeah.
Formed when these huge stars collapse.
That's the most famous example, yes. At the very center of a black hole, theory suggests there's a singularity. It's what's left after a massive star runs out of fuel and just collapses under its own gravity.
But there's another one, isn't there? Even bigger, in a way.
Oh, absolutely. Maybe the most mind-blowing one is the Big Bang. The idea is that our entire universe, everything we see, began as an infinitely dense, incredibly hot singularity. From that single, tiny point, if you can even call it a point all, of space, time, matter, energy just exploded outwards.
Wow. So understanding these singularities connects directly to cosmology, to the origin of everything.
Precisely. It links the birth and potentially the death of cosmic structures. It's fundamental.
Okay, so general relativity points towards them, predicts them even. But there's a problem, right, when you bring in the other big theory of physics.
A huge problem, yes. This is where general relativity and quantum mechanics really clash. You see, general relativity works beautifully for large scales, planets, stars, galaxies, but it predicts these infinities as singularities, infinite density, zero size, and that's where it breaks down.
And quantum mechanics.
Quantum mechanics, which is our theory for the very, very small atoms, particles, it just hates infinities. It sort of fundamentally resists them. It suggests there are minimum scales, maybe even space-time isn't smooth, but sort of pixelated, granular, meaning you just can't crush something down to an infinitely small point.
So they contradict each other right at this crucial point.
Exactly. And that clash is a massive signpost. It tells us very clearly that our picture is incomplete. We need something deeper, a theory that unites both gravity and quantum effects.
A unified theory. And physicists are working on this. What kind of ideas are out there?
Oh, definitely. This is one of the biggest goals in physics today. Ideas like string theory or loop quantum gravity. These are attempts to bridge that gap. String theory, for instance, suggests that fundamental particles aren't points, but tiny vibrating strings. Because they have a size, however small, they can't collapse infinitely.
Okay, so that avoids the infinity issue.
It potentially does. Loop quantum gravity takes a different approach, suggesting space-time itself is made of discrete chunks, like quantum units. Again, no true infinite points possible. And these theories sometimes lead to really wild ideas, like maybe the Big Bang wasn't the absolute beginning. Perhaps the universe didn't start from a singularity, but sort of bounced from a previous collapsing phase.
A bouncing universe that changes everything. And circling back to black holes for a second, there's this other related mystery, the information paradox.
Ah, yes. That's another deep one.
Quantum physics says information can't just be destroyed, right? It has to go somewhere. But if something falls into a black hole and hits that singularity, where does the information about it, what it was made of, everything, where does that go? Does it just vanish?
That's the paradox. It seems to violate a core principle of quantum mechanics. The solutions proposed are, well, they're still being debated heavily. Some think the information might get sort of smeared out or encoded onto the event horizon, the edge of the black hole.
Stored on the edge.
Possibly. Or maybe it escapes somehow during the black hole's evaporation, though how is unclear. Others propose even stranger things, like information escaping into other universes we just don't know yet. It's right at the frontier.
So really, these singularities, they aren't just weird theoretical points. They're like cracks in our understanding.
That's a great way to put it. They are cosmic signposts. They show us exactly where our current physics fails. They point directly to where the next big breakthroughs must lie.
And figuring them out isn't just about singularities themselves.
No, not at all. If we connect this to the bigger picture, understanding them, or understanding why maybe true infinities don't form, could unlock answers to the biggest questions. Where did the universe come from? What's its ultimate fate? What is reality at its most fundamental level? Singularities force us to confront those questions.
So Thinking about all this, what does it mean for your picture of the universe? Does this idea of a universe perhaps bouncing, not beginning, or information maybe not being lost but stored in ways we can't imagine, does that challenge how you thought things worked? Definitely something to ponder.